Okay, I guess we are live. Okay, so we were discussing about this information gain, though, right? Okay, does anyone have a solution to this? So, information gain, the way I understand, is basically the difference of the entropies, right? So, when they ask information gain of uh, vaccination is basically if you use vaccination as the feature to split at the root node, what will be the gain that you get, right? So at the root node, the entropy, see, entropy you will calculate for the target variable though, right? So which is malignant. So the entropy difference you'll take. So initial entropy is just the root node entropy, which is malignant entropy, which you just calculated in the second question, which is 0.9798 if I'm not wrong, right? And then is you take the so each of these so in vaccination what you will do is then you will say okay, I will split into two nodes, 0 and 1, right? And in 0 is there when you look at you look at all the possible values of malignant in that node, and then for the one branch, actually let me just write it down, no, one second. uh, Okay. See, the way I understand it, actually, I've not worked that much on decision trees. Let's see, you know. So, okay, so this is the root node, right? So we're doing question 3 of week 6. Okay, this is a root node, and we're saying if I use vaccination, so let's say 0 and 1, right? I get two children. Root node entropy is what you calculated in the second question, right? So 0.9798. Now the thing is, when you look at vaccination um, 1, when vaccination is 1, malignant is always 0, right? So you only have elements of 0 here, right? 0 always. So what is the entropy of this guy? This guy will be just 0 entropy, right? Um,
Sorry to interrupt.
yeah.
Raj, why do we take the root node as malignant? It is the question. It is not there. I think the malignant. It is not mentioned there, right? Whether it will be the root node or something from the question.
No, no. So the thing is, so what is your prediction thing right here? So basically, what you want to predict. So if you see here, age, vaccination, tumor site, all of these are some features that you have, and you're trying to predict whether the tumor is malignant or not, whether it is what do you call that? Yeah, is it bad, or I mean, is it life threatening or not? Yeah. So,
Okay, okay.
so basically, you'll calculate entropies or whatever measures you have based on the target variable, right? So here the target variable is whether it is malignant or not. Yeah.
Raj,
Yeah.
I think a question is a little bit unclear on that issue. It would have been better if the target variables are mentioned that we are trying to predict the malignancy of the tumor. So if that is explicitly mentioned, I think that would have been better for all of us. Even I was stumped working on this question first, but then I realized, yeah, this is the target column. We have to calculate the entropy for.
Yeah, I was also as it is the alone. It is their vaccination. I was thinking that for the alone, the info gain it will be like root. It is the maximum value is one minus that entropy value. The info gain it will be that way. So because there is no reference, it has been given. The target variable it is not given. So that way it was the question was little bit of trickier.
Bit unclear on that.
So that's actually I
yeah.
didn't able to get the answer for that one.
So yeah, bit unclear in that sense, but I think so. I would if see these sort of questions are present, that's fine. So I would suggest you to ask on the group, once. See, because so in this whole question, second number question, there is nothing regarding what the target variable is. So if you had just asked that, we would have cleared it. Point number one. Point number two, generally speaking, in all of these tabular sort of approaches, what you do is your last column is generally the target variable. Okay. So I mean, take it as a what do you call that, rule of thumb in some sense. But yes, I understand it's a bit unclear. So take it. I'll ask the TAs if we can ignore this question number three. Is it? Question number three. Yeah. Okay. Yeah. Anything else? Yeah, it's provided on the board. Fine. Okay, with that we'll start the today's session. So welcome to the week 8 live session of your course Intro to Machine Learning. My name is Rajvi Jain and I'm a PhD student in IISc. So today we'll talk about an issue called as class imbalance and some examples and some solutions for this this issue that we have. Um, and as usual, we are currently live streaming to YouTube also, and whatever is written will be made available in the PDF format. Okay. Um, okay. So first thing, so what is class imbalance in some sense? Is basically the situation when we have one class more when we have samples for more very high for one class compared to the other, right? So why is it a problem in the first place, right? So if you think about it, consider for example when you have 99 samples of the positive class, okay, and one sample of negative class, okay. um, and see, you can reverse the issue. You can just say one sample of positive and 99 sample of negative. Whatever we talk today is a bit more general in that sense. So you will, I mean, these are all just numbers that you can always interchange. Okay, fine. So let's say we have this sort of a number of samples between the positive and the negative class, and let's say we use the cross entropy loss because it's a two class classifier, so we know cross entropy works for such classes to train a binary classifier, right? So cross entropy, basically how it would be is you will have, for example, all the samples, right, 1 to 100, and the output of the classifier, which is the probability of belonging to positive class, that with yi and 1 minus yi into the probability of not belonging to the positive class, that is probability of belonging to the negative class, right? This is the cross entropy loss. So one solution that the binary classifier can take, and what we're saying the classifier to do is to basically just minimize this particular loss, right? CE loss. So what it'll do is it'll just say yi hat as, I mean, the output as always very high, right? It'll say, okay, just output close to 1, like 0.99 always for all the samples, regardless of whatever the sample is, whether it is positive or negative, I don't care. I'll just keep on giving a very high probability for all the samples, right? Now this will cause the CE to get minimized if you think about it, right? Why? Because when you predict yi to be very high for the 99 samples that you have, this log yi into yi when you take negative, that will be very low. The only one example, or like only one of the values among this will actually have some high value, which is fine for the binary classifier, right? Because it's saying, okay, overall I want to minimize, so if I just predict this, I will have some sort of a minimum CE loss, right? But what's happening though, right? It's basically predicting the negative sample also as positive sample, right? Or also as positive class. So exactly what's happening here is that so we also look at, let's say, accuracy, right? Accuracy is, for example, I use the threshold of 0.5 probability. So I'll say whatever is more than 0.5 probability, I'll give positive class, and less than 0.5, I will use negative class, right? So if I do this and get my accuracy, I will get like very high accuracy, right? Because it's saying positive for everything, so all the positive ones will be correct. Only one is wrong, and therefore I'll have like very high accuracy, right? But the thing is, the model is not learning anything useful though, right? Because so what is it's just saying one for all the samples, so it hasn't really learned anything useful from the data, and therefore if you go ahead and try to use this for any later usage, like try to predict something, some other systems also, it won't actually do anything better, right? So one obvious solution is get more samples of the other class, right? Because I just have one sample of negative class, so what I will do is I will say get 98 more in some sense. So I will have 99 of positive and 99 of negative. So now I don't have this class imbalance problem, right? So but it's possible, but the thing is this may not always be possible. For example, in medical data, when you're trying to predict like whether a particular person has cancer or Alzheimer's or stuff like that, the number of people who have cancer and Alzheimer's itself is very low, right? Compared to people who are healthy, or in some sense don't have cancer and Alzheimer's, the people who have this diseases are very low, right? So getting actually getting those people's data may not be possible, right? So the issue here is that the prevalence, that is the number of samples that exists in the real world itself, is very low, right? So what do you do in such cases? Okay, so people have come up with many different techniques to solve this problem. um, yeah. So one idea that people had was that we can do something called as undersampling or oversampling. So what you do is you take your whole data set, right? You have this data set with you. You construct a fake, not fake. You take a smaller data set from this. What is this? I'll basically just take one positive sample because I only have one negative sample. I will take the same number of samples from the positive class. I will only use this to train my model, right? That is one way to do it. Or other way is basically I'll basically just do oversampling of this, right? I will basically say I will replicate this particular entry 98 more times and say, okay, these are all now different samples for me. So I'll treat I'll have basically same number of samples in positive and the negative class. Okay, but the thing is that this sort of approach can go into some issues. Okay, so people have discussed about this a bit. So see, one thing is that having this one positive, one negative is anyway bad, because you actually have good amount of data with you, but you're actually just shooting yourself in the foot and saying, I will not use all the data. I'll just use some like a very small subset of it, and try to train the model, which is in any way bad, right? And the thing is, this idea of using oversampling the minority class in some sense, right, is that we'll come to it in a while, more detailed issues. The other issue is, see, whatever algorithms we apply, we assume that your X is basically IID. I mean, sorry, samples of X is IID, right? That is, they are independent and from each other. But what has happened here, though, right? Here, these 99 are not independent, right? They are all the same, right? So these sort of assumptions are actually being broken, right? So now we'll see one example in detail as to how what will happen if you do like a oversampling sort of procedure. So let's say we have like a training data in which I have 1 lakh samples, and the prevalence is 10%. So here it is negative and positive. So I basically have like 90% negative classes and only 10% positive classes. Okay. So what I do is I say go ahead and oversample it. So now what will happen is I'll have like 90,000 more samples of negative, but all of those are chosen from these only. If we're not trying to construct new data here, whatever we have, we're trying to work with that. So I just duplicate these rows in my data set and say, okay, these are also some new samples in my data, and therefore get like 50% prevalence, right? So now I have same number of classes samples in both the classes, right? And the serving data here, the serving means test data in some sense, right? So the test data has like 10,000 samples, but the prevalence is 12%, right? This makes sense because your actual test is following the distribution of trained data, right? So trained data also has like 10% prevalence, and this is about 12%, so which is like similar to what we have in the actual training data. But the new trained data has some different prevalence, which is what we are trying to hope to use it to solve the issue. Now, if you think about it, the classifier, any binary classifier, the idea is that what it will try to do is that it, it it'll try to look for some sort of a threshold sort of a thing, right? It'll say, okay, if the feature value is something like 7 point something, I will classify it as positive, otherwise negative. Okay, so if I had used, for example, a proper way of training this system, it should hopefully do something like this, right? So find the best threshold, best value on this feature to separate out these two, positive and negative classes, right? So the threshold that you would get in by using this approach, right? By using the right approach to train a ML model, whatever, you might get like around 7, right? As a feature threshold. Now what's happening here is that you will say, okay, so the classifier now sees, okay, that the crossover sort of thing is happening around this 6.2 or whatever, right? So I will use my threshold as 6.2. Okay, so now if I were to use the model trained on this oversampled training data, okay, and use this threshold to classify the points here, right, what would happen though, right? So I will have, this is like 6.2, let's say the oversampled data. Okay, is anyone unmuted? Arpita, can you mute yourself?
Yes.
Yeah. Thank you. Yeah. Okay. So the threshold when you use the oversampled data would be around 6.2, and the threshold when using this actual training data would be around 7, which is something here, right? Which is something here. This is the actual data, right? Actual threshold. So if you check now, the cross entropy loss that you would get by using this threshold versus using this threshold, which will be higher? Which loss will be higher? Any ideas? So what is cross entropy thought process, right? So you're trying to say, if a class belongs to a given sample belongs to a given class, I will use that class's probability as my loss, right? The predicted probability, right? So any idea what which threshold when I use, I'll have higher cross entropy loss?
I think the lower one, right?
The this you're saying oversampled?
Yeah, the 051. Because there are more misclassifications here, right?
Correct, right? Because if you see here, the misclassification rate in some sense is all of these points, right? And obviously these points also on this side. In when I'm using the actual one, I just have this and these, right? So I'll actually have higher loss when I'm doing the when I do this oversampling sort of procedure. Okay, so this example shows you that this oversampling sort of a thing may not always be right to do. Okay, so and yeah, so basically higher for oversampled data.
Raj, the threshold you are putting here corresponds to the Bayes optimal classifier, right?
Correct.
Sort
Yes.
of.
Yes. Yeah. Yeah.
Okay.
Yeah. Yeah, because you need to take in the priors and everything into consideration. So yeah, it's a Bayes classifier sort of thing. Okay, so your threshold from Bayes classifier. Okay, so hence, so if you think about it, like using this sort of an approach may not always be right for your data set or your machine learning algorithm, right? So that's we saw that, it may not be exactly right to do that. So the another thing that people try is to generate more samples of the minority class. For example, let's say things like SMOTs mode, which is basically synthetic minority oversampling technique. The idea here is that so let's say I have this positive class here, and I just have three negative class examples with me. Okay, so the idea is that I draw a line between any two points in the minority class, and I choose any one point on this line as my new point of the class of the smaller class. Okay, so basically I do this over and over until I get like a similar number of samples between the positive and the new negative class, right? So basically generate points using some convex combination of the minority class points. Okay, so you keep on doing this sort of a thing, right? So typically all of these so we have many more methods to generate samples from the minority class. uh, and the thing is like they all come with some assumptions in them, right? So here the assumption is that okay, these are so closely, I mean, like there is clear separation between the two classes, and hence so any point which lies in this sort of a space of this feature space may not belong to the positive class, right? So that's one of the assumptions that we have in this SMOTs technique. Okay, so for example, let's say I use this I have a set like this. For example, let's say all my positive class are clustered in the center, and I have a negative classes like this, right? So which are like all around the place. Now if I were to use SMOT, what will happen is I will for example, I will join these two lines and generate a negative sample somewhere in the between, right? Which may not be right. Okay, so this one issue. So for example, if you were to convert this into a polar coordinates, for example r and theta sort of coordinates, all of these they come down into a different sort of a space here, right? So it may work by applying this mode technique when you feature transform these your data sets, right? So the thing is like it's not very trivial to apply this SMOT technique and see whether will it work or not, right? So typically what people do is they go ahead and try the SMOT technique and see whether they have any higher like better accuracy or not, right? um, but the idea is that because of the assumptions that are underlying this particular technique, it's possible that whatever data you generate is not the right data. So therefore you're just training the ML model on some unknown incorrect data, right? So hence it's not I mean at least I don't prefer doing something like this, right? We saw this one approach. So we have one more sort of a solution here, that is basically we can learn the class conditional densities, right? So what I can do is I can try to start learning this p of x given y, right? So I can do like something like this. So I can try to learn some sort of a Gaussian thing here, and and learn Gaussian around this. And so in case you want to generate new samples, I just sample from this Gaussian, right? That's one way to do it. Or you can basically use this learned densities to try to make your ML algorithm a bit better, right? So what you can do is, for example, let's say you can model the densities, and then look at, for example, try to generate samples from it, right? So from here what will happen is I'll say okay, so hopefully this particular some point here may be negative because it's falling like in some range of this Gaussian distribution, right? Now then we have we already know that, using just Gaussian as the approximation may not be always right, right? For example, I can always have some data which has like multiple modes in it, right? Which brings issues with itself. So for example, let's say I have some data points like this, and I also have the same class. For example, let's say all is a X class, right? So if I were to fit a Gaussian, what will happen is it will say that this is the mean, right? Some sort of a mean of this data set, which is not right. So ideally, the way people have taken forward this idea is to use something called as Gaussian mixture model. Okay, this will probably have it in week 10 or so, GMMs. Okay, so the idea here is that I will basically have multiple Gaussians to model a single data set, right? So what I will do is I'll say, okay, um, I have these classes here. Okay, these are from one Gaussian, and this is from another Gaussian, right? So basically what happens is your data given this class, right, is basically a combination of two Gaussians. Okay, so we can try to do these things also, but the issue is again that we're always making some sort of an assumption on the system, right? And say in case this is not a good assumption, we basically end up losing out on the accuracy of the system, and even more so on the correctness of the system to be used in the future applications, right? So what do we do? So yeah, so basically all of these methods, they have some assumptions which we can't even validate sometimes, or they have to train. For example, the GMMs require something called as an EM algorithm, which also has the issue like in neural networks to get stuck in local minima, local maxima, right? So hence it's possible that whatever you model the density as, it's not right in some sense, right? So we have all these issues in in these methods. So basically the issue is that the ML model isn't able to get a good signal from the loss function, right? They're saying that okay, what you have done, this mistake of this plus class, I mean, you're predicting the negative class as positive class. This thing was so bad that you should try to fix yourself, right? So basically, what people do now, I mean, they do generally also, is to look at can we modify the loss functions in itself, right? So hence that's one way. And also we also need the metrics. For example, let's say accuracy sort of measures to show that whether the model has been learning properly or not. So for example, in the example that I gave before, um, we had the issue of that even the accuracy was about very high, right? Now, but the issue is that the model hasn't learned anything proper, anything useful. So now, one idea is that okay, so it's let's take this same example that we have. So I basically have 99 samples of the positive class and one sample of the negative class, and the model is just predicting everything as positive, right? So I have 99 as true positives, one is a false positive, and zero false negatives, and zero true negatives, right? So accuracy measure is basically just adding the diagonals and taking the sum, which is 99%, which doesn't show that we are doing anything good here. Point number one. Precision, recall, F1 score, all of these are also very high, right? So what's happening here, right? So hence we need something better in terms of metrics and losses to be able to fix this issue. So one possible, I mean, some possible metrics are like this. So one is called as balanced accuracy. So balanced accuracy, the idea is that you treat these positive and negative classes as independent entities. So what do I mean by that, right? So currently what you're doing is you're saying whatever is not positive, you take it as negative, right? Instead of that, I will say that each of these samples have some probability of being in the positive class and being in the negative class. For example, like how we do in multi-class classification, right? You say that, okay, I have k classes. What you do is you're trying to you're trying to see whether the probability of belonging to each class separately, right? What this means in terms of your confusion matrix, which we saw just now, was that you treat now the negative class as the positive class and try to see how does the accuracy change. Okay, so when you do that, you come up with something called as balanced accuracy, which is basically true positive rate plus true negative rate divided by 2. So this true positive rate is basically your if I'm not wrong, this is the recall, right? So it's saying true positives by true positive plus this false negatives, right? So basically your true positive rate is 1, true negative rate Tn by n in this case is 0, right? So what are we saying? We're saying that I'm able to recall all the positive examples properly, good for me, but I'm not able to recall any of my negative classes examples at all. Okay, so hence the balanced accuracy gives a score for such a system as 50%, right? Which is the right thing to do, because we're saying that the model is just predicting one value for all samples, which is exactly what a random classifier would do, right? Just predict something randomly, right? So in that sense, balanced accuracy is a measure which is actually like unbiased estimate of your accuracy of your system when we have this imbalanced class sort of a problem. Okay, so in the same spirit, we have this macro average precision idea, right? So what you do is you say that you find the precision for the positive class, which is basically true positives by true positive plus false positive. That is this particular value by this particular row. And we also consider now as the negative class as positive class and find out its precision. So here it will be 0 by 0 plus 0. So we take it as 0 by convention, right? So what will happen is I'll have 0.99 plus 0 by 2, which is around 49%, which also shows that, okay, we're not doing anything really good in terms of the model learning anything. So same thing we can do with recall, F1 square, etc. Right? So what you do is you consider this positive classes as positive. You will get this recall 100%. You will then consider this negative class as positive. Find out the recall for that particular class and then take the average over them. Okay. So that's the idea to deal with imbalanced class problem when you have to deal with imbalanced classes using metrics as your measures, right? So using accuracy, precision, etc., you can do something like this, right? Next idea is that yeah, so how do we train, right? Because the thing is that all these metrics are fine, but we need some function which I can differentiate, which I can use to train my model, right? So one approach is that you just give a weight, some weight for your positive class loss. Okay, so for example, this cross entropy loss would now become something like this. I'll say beta times whatever loss I get by for a positive class, and no weight. I mean one in terms of weight of 1 for the remaining class, and then chooses beta properly, right? So basically yeah, so beta equal to 1 is a normal CE class, normal CE loss, right? So now in our case, can you just tell me what should beta be? Should it be less than 1 or more than 1 in our case, where we have 99 positive classes and 1 negative class sample, right? So it should have a beta high or very high or low? Any ideas?
Low beta, right? To
Sorry.
low beta less than 1, right?
Less than 1, right? Correct. है ना? So So the idea is that so beta basically quantifies how much importance you want to give to the positive class. Okay, so the thing is we want to give it less importance because we're anyway doing well in the positive class because of the fact that it is highly prevalent. So we want to give it less importance. Okay, so eh, so that will be the beta value in this particular setting. So generally what people do is beta is set to something like number of the negative class samples divided by number of positive class samples. Okay, so in our case only 1 by 99. Okay, so the idea is that like you try to give weightage more to the positive class in case the positive class examples are less, and in case the negative class examples are more, I mean less, then you give more weight less weightage to your positive class. Okay, so with this idea we can train the CE loss and I mean use this weighted CE loss, weighted cross entropy loss to train your ML models. Okay, so now what will happen is whenever the model does a mistake in this this the negative class, the cross entropy loss value for the particular prediction will be very high compared to all these beta I mean all of these positive class examples, right? And hence the model basically gets a signal saying that what you have done is not very right, so can you please fix your ways accordingly, right? That's the thought process. Okay, so now we can take this idea further for multiple classes, right? For example, when you so your cross entropy loss when you have multiple classes is something like this, right? You have yi log, okay, I just use k here, yi log yk hat, where yk hat k is like 1 to k classes, right? So k basically tells you, I mean yk hat is basically the probability of belonging to this particular class k, right? Probability of class small k, right? So right, so based on which class has what sort of a distribution, we can actually give different weights for each class here, right? So we say beta k, and you give a different class for each of these give a different weight for each classes, and that to encourage the model to fit those, I mean to do better in those ideas properly, right? So this is one way you can take it further to multiple classes. That is one idea. Second thing was, can you use this idea to differentially weight mistakes, right? For example, if you're trying to let's say do something like this, cancer detection, right? And let's say I mean in such cases your positive class is basically cancer is present, right? And negative class is basically cancer is absent, right? So basically it's like diseased or healthy sort of a this one. So the thing is your let me build the so positive negative, this is prediction, right? So this is true positives, false positives, right? So what will happen when you make a false positive prediction, right? So that is the person is not having cancer, okay, but you said that the person has cancer, let's say, right? So what will happen is that person will basically end up spending a lot of money on the tests, right? Like doing more tests, so that's one thing. Second thing is the mental issue that they have. For example, now they get sad about having so and so disease, right? All of these are the downsides of having a false positive. So what is false negative downside? So for example, let's say the person actually has cancer, but your system ended up saying that he doesn't have cancer, right? What can happen is basically the person's health can get even more worse, and he may possibly even die, right? Then basically as a ML scientist, and and not talking to your different stakeholders, your hospitals and etc. You decide to say that okay, I will try to treat my system in such a way that I have as less false negatives as possible. False positives are still okay, right? Because here the alternative is very bad compared to these alternatives, right? So I'll say okay, try to have as less false negatives as possible, right? So in this case, how would you design your loss function, right? What would you do to your CE loss to help the machine learn that okay, if the person has actually cancer, predicting that person as negative is very very bad. So what you will do is you will try to give some sort of a weightage, right, again for different samples differently, right? So based upon how the machine how your algorithm performed on a given sample, you will check whether the sample then becomes either a false negative or false positive, right? And then if it is a false negative, you give more weightage to this particular issues, and try to make sure your model learns through this loss function. Okay, that's one way. You can use this idea of weighting different parts of your equation differently, so as to learn whatever you want the ML algorithm to learn. That's another idea. Second, third thing is that so we can take this idea further into regression. And so can you think about how this problem would show up in regression? Any ideas how this will show up in regression? Like because see, this is we're talking about class imbalance though, right? So what is class imbalance when it comes to regression? What is class there, first of all? So any ideas, how would this problem come about in?
Maybe,
Yeah.
maybe the class will correspond to values, right, in the domain of the output variable or something.
Okay.
I'm not sure. Maybe all the values are not uniformly represented or something.
Values are not uniformly represented. So in some sense that there is some sort of a bias, right, in the values. For example, let's say if your predicted variable, okay, predicted I mean your target variable, let's say target variable, and this is the count of this target variable or some sort of histogram or whatever, right? It follows something like this, right? For example, some beta distribution.
Skewed distribution, right? It's not
Correct.
symmetric. Skewed.
It's skewed, right? So what will happen is your MSE loss, what it'll do is it'll say okay, just predict the mean and leave it, right? So mean be somewhere here, for example. It'll say okay, just predict, for example, keep predicting high values always, right? Something like these values only always, okay. So that whatever because the number of these samples are more, the MSA loss will actually be lower, right? But the issue is that you want the model to learn the intricacies of when the target variable is also, like for example, these values, right? So by predicting just the high values, this model is not able to learn anything interesting about the the target variables distribution with respect to your input features, right? So which is basically very bad. So in such cases, we should try to solve this MSE. So instead of using MSE loss, can we use some sort of a weighted MSE loss, right? This is one idea. Second thing is, can you actually build new loss function itself, right? You can basically try to use this beta distribution idea, and can we construct a new loss, right? Which obviously needs to have things like it should be differentiable with respect to the inputs of the ML model, so that the ML model can differentiate and update its weights accordingly, right? So these are the three ideas which you can use to use to basically deal with problems of class imbalance in some more detail, right? Okay, so that is the thing. I wanted to give brief idea about something called as a triplet loss. Okay. So have you guys heard about this triplet loss? Anyone?
Yes, I have heard.
Hmm. Yeah. So
I
you
think
want
some
to, yeah.
one shot learning or something, right?
Ah, yeah. Okay.
Contrastive. Some you have to compare two faces or something. Means
Hmm.
I read something somewhere about this. I'm not sure. Yeah.
Uh-huh. Okay. Hmm. Correct. So basically, the idea for this sort of a loss came about from this thing called as one-shot learning. Okay, one-shot learning. The idea was that let's say you train a model to look at dogs versus cats. Okay. You train the model using some sort of CE laws or whatever, and you learned how to differentiate dogs and cats. Now let's say some person uses your algorithm to I mean gives as an input a monkey face. Okay, your model doesn't know monkey faces. It knows only dogs and cats. So what it'll do is it'll say, okay, this is whether it's a dog or cat, right? So basically, it'll only give some probability like this. It'll say, okay, probability of dog. Let's say dog is positive class, cats is negative class in some. Again, no bias here. So let's say it tries to model the probability of the image being a dog, right? And so what happens is this monkey image as the input when you gave, this will also get some probability value, right? Because your ML model will just take pixels and give a number, which is the probability, right? So this monkey image, it'll take as pixels as input, and it'll give some probability of it being a dog, right? Now the thing is, if it says zero, even let's say, okay, very nicely you trained, probability of it being zero, doesn't mean it is doing right? Because in his binary class classifier, what is probability of positive class being zero? It means the probability of negative class is being one, right? So it is in fact saying that, okay, it is not a dog, it is actually a cat, right? So if it outputs the value zero, probability is zero. If it outputs anything more than zero, it is saying, okay, probably it is the a cat or a dog, like based on some 0.5 probability, you'll make the decision. Okay. Now the thing is, this whole idea, I mean, this whole thing was actually wrong, right? It's neither a dog nor a cat, right? It is something else entirely. So then the question came, okay, so if you have to do like this, so then what you will ideally do, right? You will say, okay, now I will build a new classifier which takes dogs, cats, and monkeys as inputs. I mean, like three class classification I will do. I will say, probability of a dog, probability of cat, probability of monkey. So when I give monkey, so I should probably get, I should get more probability in this particular, class. So you said, okay, fine. So this is okay. You solve this monkey problem. Now somebody comes and gives you hippopotamus image as input to this particular ML algorithm, right? So same issue now again, right? So now what you will do? Now you will build four class classifiers. It. So the idea is, so the point here is that it can happen that your some random input can come to your ML algorithm which does not belong to any of your classes for which the ML algorithm is trained for, right? So you cannot keep on just making more and more complex ML algorithms, or basically keep on getting more and more data, keep on adding more and more classes, keep training your ML model over and over, right? So the idea of this one shot learning was that, can I do something, actually let me just remove the slide. So can I do something like this, right? Which says that any input uh, belongs to a given class, let's say class, the positive class, or it says negative class, or it says that it is neither, right? So can I build something in this format, right? So the thing is, this I can actually extend it to multiple classes also, because I can say, okay, does it belong to class 1, class 2, class K, or none of them, right? So this sort of an approach is what they were after. So one of the ways to solve this kind of an issue, what people came up with, was the idea of a triplet loss. The idea that let's say we have, for example, let's say cats and dogs. Okay, so let's say I'll use this once again. So I have cat one image here, cat two image, dog one image, and dog two image, and something, right? So, uh, so what they do is they actually have a ML, some neural network, which takes as input some image, right, and produces some sort of an embedding, right? Some vector representation of the image, right? This is some vector representation, right? Now the idea is that you want to want these vectors to be learned in such a way that any two samples of the same class should have less distance among them, right? So these vectors that you use to represent this cat 2 and cat 1 should have less distance among them, okay? And the vectors of this dog 1 and dog 2 should have more distance, okay? Again, dog 1 dog 2 should have less distance, dog 2 and cat 1 should have more distance, dog 2 and cat 2 should also have more distance, cat 1 dog 1 should have more distance, so on, right? So basically you want to reduce, okay, same class distance among the vectors. That is one. Second thing, also increase the distance between different class images, okay? So by doing this, we will have to try to do this sort of an approach. And so for training, they came up with something called a triplet loss, which takes basically, if I'm not wrong, I think three samples. The let's say image 1, image 2, and image 3, okay? Where they say image 1 and image 2 are, for example, of the same class, okay? So you will say reduce, so basically same class, then you'll have like minus of distance between image 1 and image 2, okay? And then add the distance between image 2 and image 3, and also I think add the distance between image 1 and image 3. So you're saying that these two are same class, so make the distance reduce. These two are different classes, so increase their distance, and increase this distance from image 1 also, right? So that's the idea. So with this, so how does this solve the issue, right? That we saw in the previous page was this. So let's say when a monkey comes into in the image, what happens is you will get vector, you get some vector, from this from your neural network, right? You will use this vector representation to check its distance against all the cat images and all the dog vectors, right? And if you say that, okay, that this distance is more than some sort of a cutoff, let's say some margin, you will say, okay, so some margin here also, right? So then you say that, okay, this vector is something new, which is different from cat and different from dog based upon this margin that I've chosen, okay? So in this way you can construct a way to basically have this sort of a classification where you say, does the input belong to a positive class, negative class, or neither of them, right? So the point of this exercise was that to make you understand that it is not just always, the world doesn't end with this two losses, MSE and CE, right? there are a whole lot more losses defined and designed with the idea that uh, where it where it is right to use a particular loss, right? So whenever you have some, a problem to solve, make sure that you're looking at the assumptions made behind these losses, right? And are those assumptions true for your data set or not? And in case if they are not, then you should look for a new loss which is which you can use for your ML algorithm. Okay. So yeah, so we'll end the session here. Any general doubts, or any doubts in this session, you can ask.
Hello, Raj.
Yeah.
I just wanted to clarify the contrasting loss case. When you learn an embedding, basically you are trying to do some sort of unsupervised clustering, right, on the data so that similar things fall into the right feature space, right?
No.
Sort of.
No. No. So the thing is, see, clustering would mean that there is no labels at all, right?
Okay.
Right.
Okay.
So
Yeah.
in
True,
clustering,
true,
the
true.
idea is that your data is the god, right? So there's nothing telling you whether these two belong to the same class or not. And the whole idea in clustering is whatever metric you choose, right? If you choose, for example, Euclidean metric, so for example, these 2 points may get classified, may become into a single cluster. For example, if you use, for example, the L1 sort of norm, these two may become different clusters, right? So but here what we're saying is we actually have a label with us which tells that, okay, these 2 points, whichever come about, for example, let's say some cat1 and cat2, right? These two, you learn their embeddings in such a way that these two are close together because they have the same label, right? So that's the big
Yeah,
difference
means
between
learning.
the.
We are learning the representation basically, right?
Correct, yes. Whereas here we
Learning the
don't have
representation.
anything to tell us whether what it did was right or wrong,
Yeah. Correct.
right?
Got it.
Yeah. Okay. Anything else? Okay. Fine. Then we'll close the meeting for today. We'll meet again in the next Saturday.